I want to revisit a couple of things again in these two podcasts just to kind of reinforce, because we've been adding lots of little pieces and it's better to just keep focusing on what evidences we already have. We looked at this before, so let's look at it again. What are the human fingerprints all over our climate? Literally, you can think of it as detective work. Let's say, as I said before, you're looking for evidence of a crime, then you try to find fingerprints, right? If you find a clear evidence, a weapon of that's used in the crime or the person, that's different, but otherwise you look for fingerprints. So since there is so much debate about climate change, we do look for fingerprints, and we know the kind of things that we expect from increased greenhouse gases. Even though temperature has not shot up at the rate that we expect from the past responses between temperature, CO2 and methane. We said CO2 and methane are increasing first and then temperature is responding now, as opposed to the past when orbital change was creating temperature change, then CO2 and methane were responding, right? So these are the kind of things that are happening. Nights are warming faster than days. There are processes that cause this in terms of loss of energy. Remember, outgoing long wave has to balance the incoming short wave, and the imbalance in this radiation coming in and going out is caused by the additional blanket provided by the greenhouse gases, which tends to have a seasonality, which gives us winters warming faster than the summer, because the summer is already warm. Already there are processes of convection, evaporation, winds, rain, ITCZ, energy moving to the north, etc., equator to pole temperature gradient, and so on, right? The seasonality came from the obliquity and so on, but it also came, the climate response came from the change in the equator to pole temperature gradient. So the equator to pole temperature gradient changes differently over seasons as well. So the response is going to be different seasonally as well. Okay? Cooling of the upper atmosphere. If you trap more energy in the lower atmosphere, outgoing long wave is imbalance, so you are putting less energy in a simple sense. There are more details which we won't get into. In the upper atmosphere, so troposphere and the surface are getting warmer, but the stratosphere is getting cooler. Less oxygen in the air because more fossil fuel is being burned. We're burning at a massive rate, many million barrels per day, yes, and that CO2 oxygen decrease is easily measured, as we saw by Ralph Keeling, son of Charles Keeling, who measured CO2, and we can find evidence of more fossil fuel carbon in the trees. What is fossil fuel carbon? Remember C3, C13 and C12. Photosynthesized organic carbon is depleted in C13 because photosynthesis prefers to take C12 because energetically that's more efficient. So buried material from photosynthesis from the past, if you burn it, you're going to introduce CO2 that is depleted in C13, and that's going to change the CO2 content in trees and the ocean and so on. So less heat is escaping to space. Again, this is a zeroth order explanation. There are more complications because remember we showed that there is an emission temperature sigma T to the fourth, which is determining the outgoing long wave. But where is that emission happening from? It happens from multiple places in the atmosphere, and those places themselves move the entire profile. Remember the tropospheric temperature profile? That itself changes. So the outgoing energy long wave at different wavelength in the long wave, near infrared and so on, also changes. So it's more complicated, but you can, in a simple sense, you can think that more energy is being trapped, less energy is going out, which is measured with satellites. More heat is returning to Earth because the greenhouse gases are getting warmed up and they reflect long wave downward as well as outward. More fossil fuel carbon in the air, obviously. More delta C13, negative delta C13 air in the atmosphere. Patterns of ocean warming, so equator to pole temperature gradient changes, winds change, rainfall changes, evaporation changes. Dry regions tend to get drier, wet regions tend to get wetter, at least on the ocean. Things are complicated on land and so on. And more fossil fuel carbon can also be found in corals. I just wanted to restate these things in a more deliberate way so that you can really remember. And this map we saw, let's revisit again by looking at the number of pieces of evidence, which I didn't mention before. Okay, so here over North America there are almost 10,000 pieces of evidence. Far fewer in South America, close to 2,000, about 3,000 over Africa, more than 10,000 over Europe. Longer history, longer records, longer instrumental, historic and other records, and so on. We don't even mention over the Arctic and Antarctic. Okay, more than 8,000 over Asia, again cultures that have lived for long. And or Australia, which is much more recently colonized, about 3,300. Okay, this number keeps changing because each year we are accumulating more and more evidence, obviously, right? So what were we looking at? Using all these evidences, scientists IPCC has compiled Intergovernmental Panel on Climate Change, which has hundreds of scientists working together producing a report every 7 years. The new one coming out in 2021 does a lot of this work. Massive coordination, massive model simulations, massive synthesis of published reports and so on, and they put confidence on it, right? Very low, low, medium, high and very high confidence. So these bars here you see, they correspond to various levels of confidence in the changes we see in physical systems like glaciers, snow, ice, rivers, coastal erosion, sea level effects, and biological systems in terrestrial and marine ecosystems. Wildfires, obviously complicated because humans try to control wildfires, which actually can make things worse in some ways by not burning out the dry fuel. But climate change dries the soil faster because if the air is warmer, soil moisture is lost quickly, which makes the trees drier. Trees lose their moisture quickly as well. So places like California are getting warmer. They are climatologically drier. That's not a very heavy rainfall region. Remember the cold California current and dry climate? It's basically a desert, but population is very heavy. Human habitation is very heavy. Lots of economic activities, people living closer to the woods and so on and so forth. So the human impact is included in that, but we also look at human and managed system like food production, livelihoods, health and or economics. Okay, so the impacts are identified based on availabilities of studies across the region. So the main point, just to repeat, even the polar regions, which are at least the Southern Ocean is far from human activity other than the few colonies on the glaciers in Antarctica for geopolitical reasons. If the glaciers melt and there is a lot of fossil fuel available, everybody wants to have a piece of this resource. Even though it's not good to burn fossil fuels, we are still looking for potential fossil fuel resources under melting sea ice in the Arctic as well as potentially melting glaciers in Antarctica. Human beings, we never stop looking for more resources, right? So every continent has changes in every system, physical, biological and human managed systems, human and managed systems. With various levels of confidence we can say these changes, we can document these changes and claim confidence from low to a high. Right? that's the main point I wanted to make. I wanted to kind of reiterate this before we go on to other concepts that are necessary to visit for continuing our story of oceans and climate change.